of Minkowski spacetime. I will try to finish it today, but probably we will need 30 more minutes, so we will finish it next day. So essentially, we were just building the theory the standard way, as you can find in any textbook. That was section 2. Section 1, we reviewed the classical theory, for those of you who are not fully familiar with that. And a good summary of the quantization is written here, which we have all the mathematical elements that we needed to build the quantum theory. So what one does is one takes SC, the space of complex solutions to the wave equation, and one splits that in two subspaces, one made of positive frequency mode and the other one made of negative frequency mode. S minus is complex conjugated of S plus. We have a basis in that subspace made of couples of positive and negative frequency modes, one for each value of the wave number k. And we have an inner product on SC, which is almost an inner product, but it's not definite positive. However, it is definite positive in S class. Remember, we built it, we wrote it using this conserved current that one has naturally in the Klein-Gordon theory. So because it was conserved, that was the key element, the key property to build the inner product which doesn't depend on time. And then once we have that, quantization is straightforward. Field operator is a linear combination of our bases, where the coefficients have to be operators by consistency. Momentum operator is the derivative. And one can obtain the creation and annihilation operators just by the product of the basis and our field operator. And one can check that canonical commutation relations imply that A and A dagger satisfy commutation relations of creation and annihilation operators, except for this 2 pi cube delta function that appears because we use non-normalizable modes. Then the Fock space, the vacuum is the state annihilated by all A, and the one particle Hilbert space arises from it, and the Fock space arises from it. So we have our theory, and then what we wanted to study was energy and momentum in that theory. So first, energy. We took the classical Hamiltonian, we write it as an operator. We can substitute the expression for the operator, the phi operator and pi operator in terms of creation and annihilation operators, manipulate it and get to this expression. Or the second one, where I just use it, the commutation relations there. And so the interpretation of H is that, it is the number operator times the energy of each mode times the zero energy for each for each mode. And the problem we found is that this guy is doubly divergent. So first of all, we describe the first one. It is divergent because, because the last term is doubly divergent. On the one hand, because this commutator is just A of k commutator with A dagger of k, so that is a delta of 0, and then that delta of 0 diverges. And I was arguing that, explaining that this delta of 0 is just a manifestation of the infinite volume that we have in a space. So the statement here is that, if we have a space which is infinite, and we have a quantum state whose zero energy, whose energy is homogeneous, if it is not 0, it's going to be infinite, because if the energy density is different from 0, the integral of something non-zero along the whole space is infinite. But this is, we could expect that because we are working with a non-compact spatial slice of the spacetime, and the solution, or a way of just getting rid of that infinity from our equations is just working with densities. So dividing the energy by the volume and working with energy density. If that is fine, then we are happy. There is a second divergence which is quite. So this is where I stopped last day. So I begin with new information here. So there is a second divergence which is quite different from this one. This one, because it has to do with the fact that the space is infinite, it is normally called an infrared divergence. So because it has to do with the fact that the space is really infinite. However, the second divergence is what we call an ultraviolet divergence. And this second divergence is the following. The statement here is that, even if we work with energy density, that is, if we take this integral that we had here, so the second term, what we call the vacuum energy, and we divide by the volume, so we take the volume out, this integral diverges. Diverges for simple reasons. If the vacuum energy for each k is finite, and we have infinitely many k's, when we sum all of them, we get an infinity. So that is the origin of I think I didn't forget 1/2. I think there is a 1/2.
And there was
Okay, so that is a problem. So this divergence is just a direct consequence of working with fields. In a field we have infinitely many degrees of freedom. Each degree of freedom is like an oscillator, contributes with 1/2 of h omega to the vacuum energy. We have infinitely many, that is divergent. And this divergence, this kind of divergence appear everywhere in field theory. This is one of the main problems in field theories, as I discussed last day at the very end. And it appears in free theories, it also appears in interacting theories, it appears in flat, in curved spacetimes. Just because we have infinitely many degrees of freedom, this divergence appears everywhere. So our task is to be able to mathematically manipulate that infinity and extract physical consequences from our theory. And as I said last day, the mathematical techniques that we use to manipulate those infinities and get rid of them are called regularization and renormalization techniques. So what we have to do is to renormalize our Hamiltonian. And I also mentioned that last day. So the idea of how to renormalize the Hamiltonian is the same as what we use for the harmonic oscillator. For the harmonic oscillator, we didn't need really to do it because everything was finite. But remember that the statement there was that the energy itself, in the absence of gravity, is just a convention, the absolute value of energy. What appears in physical processes is differences of energy. So we are free to rescale the energy of the vacuum and just said, by definition, that the energy of the vacuum is equal to 0. So the statement here is that in Minkowski spacetime, with Minkowski what I mean is no gravity here, we are free to shift the origin of energies. Such that the energy of the vacuum is 0. And this is what we are going to do. This is all what we need to do to get rid of that infinity. So as for the harmonic oscillator, the renormalized energy operator that we are going to call H hat with 2 dots, where the 2 dots are going to indicate the renormalized operator. Is defined from the Hamiltonian we have there by simply removing the vacuum energy. So renormalize Hamiltonian. Definition. Yes, the Hamiltonian operator minus the expectation value of the Hamiltonian in the vacuum. So this is a number, so we have to multiply by the identity operator. Obviously, this operator has 0 expectation value in the vacuum, because we will get here just 1, and here the vacuum expectation value, so this will be 0. So this is a well-defined operator. And if you go to our old expressions, you can see that all what this term is doing is removing the term that we have with the commutator of A and A dash, removing this 0-point energy of each oscillator. So the expression for this guy, Q A dagger K A times H omega. I think that's no way. And this is called the renormalized Hamiltonian. So also note that, since the vacuum energy is 0, we get rid in one step with the 2 infinities. So we don't need even to work with densities now, because the energy of the vacuum is equal to 0. So the 0, if you integrate 0 along the whole space, is still 0. So in one step, we got rid of the 2 infinities. So we are happy. So we can still work with total energy. And now I just wanted to tell you that this renormalization prescription goes under the name of normal order.
This number operator.
No, I think
H bar omega or just delta?
no, because the number operator is defined as h minus 1, this guy. So if you put the number operator at h, will appear there. And you can check dimensions. I think this is right. You can just count dimensions, and we need to have dimensions of energy. If not, that's H bar. But I think this is the way it is.
No, there is one H bar there, no? So there should be.
Yeah, earlier in the notes I have an H bar there.
Because I forgot one here. There is no here. I forgot one here.
Okay.
And then this appears because the number operator, remember, is this is the number operator. So I took H bar outside to have here the number operator.
Okay.
So that is what there was missing one there. So just tell you that this technique is called normal order, and this Hamiltonian is called the normal order Hamiltonian. The reason to call it the normal order Hamiltonian, so the reason is because subtracting the vacuum energy is equivalent, at the practical level, in concrete calculations, subtracting the vacuum energy can be implemented by just taking the equation, for instance, equation 5 that we have here. So the Hamiltonian where A and A daga appear, and making sure by hand that A daga appears before than A in any term. So changing the order by hand in all terms, inside that A daga appears always before than A. So normal ordering this Hamiltonian would be, this is okay because A daga is before than A, this is not. So we have to change that. And the statement is that subtracting the vacuum energy is exactly equivalent to change by hand this order. This is why this Hamiltonian is called the normal order Hamiltonian.
So that just means all 8 daggers are to the left of 8.
Exactly. This is called normal order operator when all 8 daggers. And you know, because the subtracting vacuum energy equivalent to have all 8 daggers. So to change by hand all 8 daggers to the right, to the left of A's. So if you want to convince yourself that this is true, so as a check, you can take a term like this, A of K, A dagger of K. So this, for example, the term that we have there. Subtract the vacuum energy, so the vacuum expectation value. So you take this operator and you subtract the vacuum expectation value. And then you can easily check the following. So if you take into account, everything is an operator. I am forgetting already all the hacks. So if you take into account that this expectation value is, we can easily compute it by using the commutation relations. So this expectation value, in fact, is the same as A dagger, A dagger. Just this will get 2 terms, A dagger A plus minus plus the commutation relations. The A dagger A is 0 because A annihilates the vacuum, so we get this. And this is, this guy is A dagger minus A dagger A. This one cancels this, and we get A plus K A. So you can see that is true, my statement is true, that subtracting the vacuum expectation value is equivalent to change the order.
Normal order still applies even for different values of K, right?
Yes. Then they commute, so you can move them freely. You don't have to do anything.
Sure.
Because this guy will be 0 in that case, because they commute. So the non-trivial effect is when they are the same. And you can see in this simple example that this is precisely true. And therefore, subtracting vacuum expectation value is equivalent to normal order. Okay, so now we have our renormalized Hamiltonian, and we can compute energies, and everything is finite, and we are happy. So when we have any other operator which is quadratic or higher order in the field or the momentum, like the Hamiltonian is quadratic in the momentum and the field, we will also find this type of divergences. So every time we find an operator which is quadratic, cubic, fourth power of phi or pi, this kind of divergences will apply.
Does this take care of the second type of divergence? Because what we're left with, we still have one term which is integral over k from minus infinity to. So are we sure that that integral will not be?
Good. You can see that this is precisely, this is the integral of differential number operator times the energy of one mole. I am just using that the differential number operator was defined as h minus 1 a dagger a. So if you apply this operator to a state which has a finite number of excitations, the result will be always finite. And of course, a state with an infinite number of excitations do not belong to our Hilbert space. So the answer is yes.
VEV is vacuum energy what? What is VEV?
Vacuum expectation value.
Oh, okay.
So I was saying that these divergences appear in any operator which is quadratic or higher order in the fields and the momentum, And the way of solving this divergence is exactly the same. You normal order that operator. So I'm going to show you a second example for the momentum operator. So the momentum operator, if you remember classically, the momentum operator was given by an integral in space, given an inertial frame. This is a vector 3 momentum operator of this density. So it's again quadratic in the field operator and its momentum because it has one power, two of them. And what we want to do is to quantize this guy, so to bring it to an operator. And if you take this expression, substitute, so expand pi and phi in creation and annihilation operators, and manipulate it a little bit. You can also check this. The exercise is completely the same, analog to the Hamiltonian one. So if you did the other one, this is just doing the same. And the result of that manipulation is that the momentum operator can be written as A dagger of k, A of k, plus A of k, A dagger of k, multiplied by k over 2, integrated over all k. And again, we can use the commutation relations to write the last term as, I'm doing just the same, used commutation relations here. You will have a two of those that cancels this. I am taking h bar outside, A dagger k, A of k, plus 1/2 of h minus 1, the commutator A dagger. The same as before, this term is also divergent for two reasons, because this commutator is a delta of 0, and second, because even if we work with densities, this is finite, so the integral for all case of a finite quantity will be divergent. So what we have to do is to renormalize the momentum operator. So the renormalized 3 momentum is just given by doing normal order of this operator. So h bar k, or doing normal order here, so changing the order of this guy, or removing the vacuum exterior value. So A dagger of k, which is the same as the integral of the differential number operator times the physical momentum. Hk is physical momentum and has dimensions of momentum. So this just counts the number of quanta and give a momentum h bar k to each of them, as we can expect. Therefore, just from this simple expression, we see that, if we want to know what is the momentum of the vacuum, that is easily computed. The momentum of the vacuum is 0, because the number operator acting on the vacuum gives me a 0. You can compute what is the 3 momentum of a one particle state. So a state with just one excitation in the mode k. That in this integral will give me 1 hk, so this will be equal to hk. So one particle states have definite momentum. They are eigenstates of the momentum operator with momentum h bar k, as we could expect. And you can also repeat the exercise for excited states, so a state with n1 quanta with momentum k1 dot 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 and m quanta with momentum mk. And if you do the exercise, you will get n1 k1 times h bar k1 plus dot 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 n m km h bar, as you could expect. Any question about this normal order operators?
What's that symbol in the second line? P acting on.
P acting on
What's the symbol inside?
1 sub k. So a state with one particle in the mode k. Any?
So that's just a dagger on vacuum. A dagger K on vacuum is 1K.
Yes. Over root square of h bar.
Oh.
And root square of n factorial, but n is 1. So. Okay, so now we have our energy operator, our momentum operator, and we know how those two operators act on our Hilbert space. So you may wonder why I am going over all this. So the reason is that, so as a conclusion of these two exercises, therefore, we have seen that the states of this type so states with one excitation, they have both. They have definite energy equal to h bar omega. So they are eigenstates of the energy operator and definite momentum. So they are eigenstates of the momentum operator. And these eigenvalues are such that if you take the energy, square it, and you take the momentum and square it, you get precisely the mass square of the field. Remember what omega was? Omega was defined as root square of k squared plus mu squared, and mu squared, mu was just mass over h bar. So if you do this, so you are recovering the dispersion relation of particles with mass m. So as a consequence of this, we have all the right to call these states as states representing physical particles. So in other words, this is the argument that makes us to call this state one particle state, because this excitation has definite momentum and definite energy, satisfying the right dispersion relation for a particle with mass m. And you know, as you probably know, this is precisely the way in which particles appears in field theory. Excitations of the field precisely behave as particles. More precisely, you know, what one would say is that the one particle Hilbert space carries a representation, an irreducible representation of the Poincare group, and that is the definition of particle that Wigner gave for us. That is just a more technical way of saying the same. If you don't know about irreducible representation of the Poincare group, that doesn't matter. But this is the way in which particles appear in field theory. We have a field, we create excitations, and these excitations behave as a state with definite momentum and energy, satisfying the dispersion relation. This is what we call a particle. That's all. Any question about that? So for those of you who have never seen quantum field theory, this point is important, to realize how particles appear in QFC. Okay? So let me go over the next section, which is kind of short. Is for the role of point guard invariance. And here, what I want to do is to emphasize the following point. So, we have constructed this field theory, and what I want to emphasize is that the previous construction, the construction of the quantum field theory we have seen really relies in, or rests on an initial choice that we made of an inertial frame. So if you see your notes, take a look to your notes, you will see that I have used an implicit choice of a single inertial frame all the way through the end. For instance, spatial Fourier transforms. So the first time I Fourier transformed the field, I was using the x coordinate of a single inertial observer, of a given frame. Uses the chosen inertial frame. Second, the basis that we have chosen in the space of complex solutions, the positive and negative frequency modes, they are positive frequency and negative frequency with respect to a given inertial frame. They are I omega t, and that t makes reference. So they are positive and negative frequency modes with respect to that frame. Third, an A dagger create and annihilate, or annihilate and create quanta with energy h bar omega and h bar k, again with respect to that frame. So remember that the definition of the momentum operator and the energy operator, they are with respect to one frame, because one needs to integrate on a given spatial hypersurface.
Is there a word missing on the second one?
In which line?
The basis of the set VR.
The
The
basis
II.
The
Well,
basis.
the basis of that
R.
VR. Okay, that's just not what it is. That's what I thought.
Thank you. Talking and writing at the same time is hard. So therefore, because all this construction rests on a single inertial frame, the vacuum, the one particle Hilbert space, and the Fock space are attached to that frame. So all our construction. So therefore, the vacuum, one particle Hilbert space, and the Fock space, the entire Fock space, have been built using this particular frame.
When you transform to the frequency domain, you're removing the time dependence, right? But does that say that particles are not created at a particular time?
Say it again.
Okay, so when you transform from time to frequency domain, right? You're removing time dependence.
Yes.
But does that mean that particles aren't created at a particular time? They always exist?
I mean, here we are, I haven't written yet any process in which particles are created or annihilated, so that question is not still on the table. What we have said is that we have a Hilbert space with the states having 0 particles, 1 particle, 3 particles, etc. So in concrete processes in which there are interactions and particles arise, you can wonder at which time those particles are, and there is a clear answer. But that question is not still on our.
Okay, so when you say that they're creation and annihilation operators, that's not quite right in the sense of them being created or annihilated.
I mean, this is a mathematical statement that you
Relative
have an
to-
operator that acts on a state and adds a quantum in it. You can call it a creation operator.
It can't be added because there's no time before or time after.
But I am not talking a process in which in which you start with no particles and they are created. We will talk about something like that. But these A and A DAG operators are just operators defined on a Hilbert space. They take one state and adds a quantum in it. The other one annihilates one quantum in it. So I think there is no ambiguity there. So
Okay.
your question is good, but we need a process in which the number of particles change in order to ask when they are created. Here they are just mathematical, and we are in a free theory, so there are no interactions. So
Okay,
I have a quick question, actually.
Please.
I was still writing things down when we were talking about these states representing physical particles. I can understand the justification that we now have states which emit definite energies and momentums, but I'm still a little bit disconnected from a statement about the real world or doing an experiment. So I'm not quite sure what it means to say this state means something in the laboratory, for instance. I'm just getting a little bit lost in the math of what I'm creating as far
Mhm.
to how it's even applied to anything right now.
right, because I am going fast.
Yeah.
But in a course on first course on field theory, then you have to explain that how do you detect a particle?
Yeah,
What you
I
have
don't
is a
even
particle detector. It's some system, I don't know, an atom with 2 energy levels that when a photon comes, is going to excite this guy and go to the upper state. But the energy levels, they have a gap in energy, delta A, and only if the photon has energy delta A, it will be excited, and your light in your detector will
Oh, okay, so we can detect these differences in energies.
exactly, and
very
this is the kind of stuff that we detect and what we call particles. So
Okay.
we detect stuff with given energy, with given momentum,
Mhm.
and therefore the dispersion relation defines for you what we call the mass.
Okay.
So this is what we call particles. As I summarize in one line, there is a more rigorous definition of particle
True.
using group
Well,
theory.
we also talked about some limitations of what we just created because it describes only bosons right now.
Right.
So this theory is good for detecting energy difference from photons and things, I
I
guess.
mean, a photon is described by a vector field, not by a scalar field, but you can repeat the process. Even
Okay.
for fermions, you repeat the process and you realize that your Hilbert space is made of quanta with definite energy and definite momentum.
Okay.
Of course, you know that a state which has definite momentum is completely unlocalized in a space.
Mm-hmm.
This is where these delta functions, these Dirac
Ah.
deltas appear everywhere. Physically, we never have sharp momentum. We already have some distribution. Right. So this is the same. But this is what we really call particles in physics.
Okay.
And in field theory, again, they arise as quanta of our field.
So
I
when I'm
remember the
doing-
first time I realized about that, I was extremely happy.
So when I'm doing a small experiment detecting particles, I really am playing with them, something like this.
Yes, exactly. So, in field theory, everything are fields. And particles appear in the game as quanta of a field. You can hit your water surface with a stone, and you create wiggles. Those wiggles are particles. You quantize them, and they are just real particles. I forgot to say that you can also show, you can also use the group of rotations to show that this quanta has zero spin equals 0. I haven't done it, but you can just, the same way I define momentum, you can define angular momentum, take normal order, and show that these quanta are bosons with spin equals 0. So they are really scalar particles. I didn't do it because of time, but the exercise is just the same. And now I am explaining something that I believe is significant, and it's the following remark. We have built our theory using a particular inertial frame. All what we have done rests on that particular frame. So the question that you should ask is, what happens if we use a different inertial frame?
Do we have an equivalent here if we use
Exactly.
another one?
Do we get the same theory? Do we get a theory which is just equivalent? Or we get something which is inequivalent, a different theory? So that is an important question. So relevant question. If we repeat the construction, with a different frame, different inertial frame, do we end up in the same theory, or something physically, mathematically equivalent? You all expect that the answer is yes.
I hope so.
We hope so. Why? Because Poincaré symmetry, Poincaré is Lorentz plus translations. Poincaré symmetry is a symmetry. Poincaré group is a symmetry of our metric of the Minkowski spacetime, and any reasonable quantum field theory based on inertial observers in Minkowski spacetime should keep that group as a symmetry. So we expect that if we use Poincaré transformation, we should get the same theory. But is that the case? How do we prove that? So
I expect that it would work because cyclotrons work.
we can prove this in two ways. We can repeat the construction using a different frame and see if the two final results are the same, or equivalently. I can do that, and in fact, I will do that more explicitly in next chapter or in 2 chapters. But it is equivalent to show that this construction, our vacuum, our one particle Hilbert space, and our focus space are invariant under Poincaré transformation. So what I'm going to do is to take this construction, these 3 elements, vacuum, one particle, and fog, apply a Poincaré transformation, so translations, spatial and temporal, rotations and boost, and see if these 3 elements are invariant or not. If they are invariant, that is the statement that our theory is the same for any inertial frame. So this is just what I said. I don't write it. So we have to. Let me start with temporal. So the Poincaré group. Poincaré group, remember, is translations plus Lorentz. So for temporal translations, they are generated by H. Remember, the operator that generates time-like translations is the Hamiltonian. And we know that this is infinitesimal. This is the generator, the operator that generates infinitesimal transformation. We know that the normal order Hamiltonian acting on the vacuum is equal to 0. It annihilates the vacuum. Therefore, if we apply a finite transformation to the vacuum, do you know how to obtain the finite transformation from the exponential? So I a hat delta t. This is, therefore, this is what I call the unitary operator implemented that translation. You know, if you expand the exponential, this is going to be 1 plus Hamiltonian square, Hamiltonian cube. Any power of the Hamiltonian annihilates the vacuum, so only the 1 will survive, and that will give me the vacuum. So vacuum is invariant under time translations. And because the vacuum is invariant, you can also check that the one particle Hilbert space is invariant, and the Fock space is invariant. I don't do this in detail, but the proof is straightforward.
So, okay, I follow why we would set the propagator as equal to IH
Which
bar
propagator?
delta T.
This,
That, but I don't get how you get that that's equal to 0.
no, this is equal to the vacuum, not 0.
Well, vacuum.
So the exponential will be 1 plus h squared plus h cubed,
Oh,
etc.
okay.
H annihilates the vacuum, so the only non-zero term is the 1. 1 times the vacuum equals the vacuum.
Okay.
The exponential of any operator who annihilates the vacuum is gives you the vacuum because of the 1. So the same can be proven, the same happens for spatial translations. So spatial translations are generated by the three momenta. The three momentum annihilates the vacuum. Therefore, the unitary operator implementing finite translations leave the vacuum invariant.
So does this all mean that normalization is important? Like without normalization, we won't have Poincare invariance, or we will still have Poincare invariance?
Why do you say that?
And like because we are getting this 0 after this renormalization, right? If we don't renormalize, we won't have this 0.
Right, but in that case, we don't even have Hamiltonian, a well-defined Hamiltonian. So we need that. But you can ask the same question in the harmonic oscillator, where to renormalize for convenience. But in that case, the only thing is that the invariance is a bit more hidden, not as explicit. But of course, the invariance must be there. Doesn't matter, your definition of zero energy shouldn't. But here the problem is more serious. If you don't renormalize, you don't even have a well-defined Hamiltonian. So.
But isn't it like infinity minus infinity? So is it necessary that if we don't renormalize, we have invariance? Like mathematically, like if we don't have this renormalization, then will we have invariance? Because mathematically, what we are doing is like calculating infinity minus infinity, right? Which is not
Right.
itself
Right.
proper. So like not having like without renormalization, do you think like we'll have Poincare invariance, or we may not have?
I think we will have them, but in a more obscure way. Of course, if your vacuum has some energy with respect to you, you have to think how that translates under Lorentz transformations. But because you know that the energy doesn't play any physical role, there should be always a way of doing it. So. But one has to be careful with the Hamiltonian, because you have to make it well defined, otherwise. So I was saying that the same happens with the momentum. You can prove that the unitary operator implementing spatial translations, which is acting on the vacuum, which is just e to the I renormalized t delta x on the vacuum, is also the vacuum. And you can do also the same with rotations. I don't do it, but you have to do the same. You have to take the operator, the classical angular momentum, elevate it to an operator, normal order, and act on the vacuum and show that it annihilates the vacuum. So for boost, the same result, the same method applies. Now we have to use the generator, the boost generator that I defined classically. I think I was calling it K. You have to make it an operator, again, normal order, and act on the vacuum. A shortcut, you can do it this if you want, but let me show to you a shortcut. A shortcut is to realize that if you have a boost in direction n with some velocity beta, and you act on the annihilation operator, so this is the way that you transform operators with u minus 1 here and u here. If you do this, you will get something proportional to A with K prime, where K prime is K boosted. So it's the K after boosting K.
That K is not related to a previous case, right?
In what sense?
This new boost K.
This guy is a capital K.
Okay.
It's a capital K was using in the talking about classical field theory. Is the generator of the boost. So the statement I am making is that one can check that this is true. For instance, you can take the field operator, which we know is a scalar, and the field operator is A e to the minus I omega t minus kx divided by 2 omega plus the Hermitian conjugated. You know how a scalar mass transform under boost. You know how this function, which is a scalar function, mass transform under boost. It's not difficult to realize how this d3k mass transform under boost. So from this information, you can get how A transformed under boost, and you will get this with the coefficient there, which is a ratio of omega over omega prime, something like that. But just for this short discussion, all what you need to keep in mind is that the boosted A is proportional to A with some boosted wave number.
So the wave number changes when you boost.
Exactly.
Okay.
So it's like this is like a momentum in units of h bar, so you get the boosted momentum. But the important thing here is that you don't have contributions with A dagger. You get something proportional to A without contributions from A dagger. That is the important thing. As a consequence, of this equation, I don't remember which name I was giving to the equations. The vacuum is invariant under boost. Remember, the vacuum is the state annihilated by all A dagger K, by all of them. So if A transform in a different A, but still an A, the vacuum that A that all A's defined before the boost and after the boost will be exactly the same. This is why it's very important that we don't have any A dagger here. If A dagger would appear there, the vacuum is not invariant under boost. But because no A dagger appears here, the state annihilated by A's and by boosted A's is exactly the same. Is that?
Yeah, like what does it mean to go from like 0k to 0 scalar like number?
Say it again. Going.
When we act this k to this 0k, right?
Here?
Yeah. So when we add this a operator on that, then it will is equal to 0, like just a number, right? Real number. So what does that mean? Like we are going from 0k, like 0k itself is like we have nothing, right? I mean it is
Right. So 0 is not even the vacuum.
Yeah.
Just
So what does
0
that mean?
in the focus space. We will give a more mathematical precise definition when we define focus spaces. But you're right, it's not vacuum, it's 0. It's not even, it annihilates the vacuum. So we will go over that. So is that clear? So therefore, the vacuum is invariant under Poincare with the sub regarding one particle states do you think that one particle states are invariant under the Poincare group?
It depends whether or not they have a beginning.
I don't think that's relevant,
Yeah.
but I don't think so. Because I could, through a Fourier transform, define what it means for a particle to be at one location, and I feel like if I boost somewhere else,
Right.
then
It's better if you think in momentum space because we have our basis in momentum space, but the same argument applies.
okay.
If you have a particle with momentum k,
Oh, if I
and
boost somewhere
and
else,
you boost it, we'll have a momentum k prime.
Mhm.
So the vacuum doesn't have momentum, so if you boost it, you will still get the vacuum.
It's
But
like
the one-
redefining velocity, so then it's
Right.
different.
So one particle state, you can see from here that A dagger will go to a dagger with different momentum. So a particle with k will go to a particle with k prime. This equation is showing that to us. So a one particle state is not Poincare invariant. But what about if you take all particle states as a set?
Then it's
Yeah, it's
invariant.
And then it's invariant because this guy will transform to this guy, but this guy to this guy. You are just shifting all of them, and you have infinitely many. So the one particle Hilbert space is invariant as a set, and therefore the focus space is invariant. So the statement here is that we could have arrived to the same theory regardless which particular inertial observer we start with. The final focus space, the final vacuum, the final notion of particle is exactly the same no matter which inertial frame you use. For this reason, the vacuum is called the Minkowski vacuum. And the focus space we have constructed is called the Minkowski focus space.
Okay, this representation of 0 is one particle. I mean, the vacuum which you are writing as just 1 0, it is one particle or?
No, this is the vacuum.
Yeah, I mean like for say two particle we write like vacuum like 0, 0 or is it like,
This is, if you want, this is 0 particles in any entry you want to have. So imagine that you are thinking about an entry for quanta with momentum k,
Yeah.
with momentum k1, k2, k3. So vacuum is 0 everywhere.
Okay. All
But because I have a finite board, I just put 1, 0, and that's all.
okay. And one particle, how do we represent? Like this?
I represent as one particle with momentum k, which is just a dagger acting on the vacuum through the square of h bar. Two particles, I represent it with 2 k's if they are the same k. If they are different k's, then I add a comma here.
Okay.
So imagine that a state has entries.
Yeah.
You know, a state is always a linear combination of all possible particle states. So it has entries, one for each k. So you have to tell me how many quanta you have on that k. So, you know, if I write that, I would need an infinite board because I have infinitely many quantas. So whatever is not here is just 0. Okay? So this is important. So this is the reason why all this construction is consistent.
I'm sorry, that curvy F is the Fox
The Fock
space?
space,
Okay.
which is our Hilbert space.
And we just refer to it as the Fox space because everything gets matched with itself.
Exactly.
Okay.
And the Minkowski vacuum. So just to finish this chapter, I'm going with some detail here because this is important for core spacetimes also. So it's good to spell it in some detail. And also important in core spacetime is correlation functions. And this is the last section before we start with time-dependent situations. You know, in order to explain with some minimal detail correlation functions, I will need a whole chapter on them. You know, they are a whole wall that you can describe a lot of details. Both correlation functions and green functions or propagators. You know, if you want to know more about it, you can check books in the literature. Fullin's book on quantum field theory has some decent amount of detail, but you know, this is a whole theory. So I just want to briefly summarize it and remark the most important points. So, you know, correlation functions, they are expectation values of field and momentum operators. All evaluated at different points. So, for instance, an example, if I use the vacuum, but I don't need to use the vacuum, I can use any other state. I can have, you know, the product of two fields, one momentum and another field. This is a correlation function. In this case, a vacuum correlation function. So they provide a quite important amount of information of our theory and of our state, the state that we are using. You know, they, as the name indicates, they provide correlations or mutual information between different points in a space for that state, or you know, or entanglement if you want for the quantum state. So what happens? This tells you what are the mutual information, the quantum entanglement between the state that you are choosing. In this example, just the vacuum. Normally they are divergent where the points, two of the points coincide, or even when two of the points are related by a null interval, with the Minkowski metric in this case, they blow up. So they are really defined as distributions. So keep that in mind. I will describe it in more detail later on. But they are really distributions, not well-defined functions. And among all of them, in a free theory, what we call the vacuum 2-point function is particularly relevant. So vacuum 2-point function. Remember that I keep forgetting the operator, so there is a hat all the time. So vacuum 2-point function, the 2-point function is just, as you can imagine, 2-point function. Remember that x without anything is 4-dimensional point. So these are functions of in the whole Minkowski space. So they are important. They are relevant for many for different reasons. So first of all, you know. So from it, in fact, we can construct, you know, what I want to say is that any vacuum correlation function with more fields can be obtained from this one. From it. If we have an odd number of fields, what happens? We get 0. You know, if we have an odd number of fields, each term has an odd number of creation and annihilation operators. So you will end up annihilating the vacuum, this vacuum or this vacuum. And for an even number of fields, who knows what happens? They can always be written as sums of products of 2-point functions. So for instance, as an example, if you have the 4-point function, x1, x2, I'm going to forget about the hats all the time, 3, and x4, one can check that this is the same as, let me just write it in a short way, you know, this is the same as phi 1, phi 2, phi 3, phi 4, where this indicates x1, x2, etc. Dot, sorry, plus phi 1, phi 3, phi 2, phi 4, plus phi 1, phi 4, phi 3, phi 2, phi 3. So all the possible combinations of couples. You take 1, 2, 3, and 4, you take couples, all possible combinations, and this is what you get. You can check that that is true, and that generalizes for any number of
Phi
fields.
one field, or are there 4 different fields? Phi one.
No, they are. This is just a shorthand.
Okay, 4 or 5 being valued at 1.
Yes, no.
But when we say there's more fields, that means there's more functions like 5.
There's more points.
There's more
So if
points.
I have you know, more phi x5, phi
Oh, okay.
x2, so
Okay, sure.
this is what I mean. You have the 5-point function is 0. The 6-point function is products of 3 2-point functions with all permutations, etc., etc. So from the 2-point function, we can get every correlation function. And the statement is that this is true only in the free theory. So a theory with interactions, in a theory with interactions, it is not true that the 3-point function is 0 and that the point function is just this. So in a theory with interactions, you have more possibilities. Just, I don't know if you have ever studied statistics with random fields, with statistical fields. Sorry. So these properties that the odd point functions are 0 and the even ones are just products of the 2-point function, this already happens for random fields which are Gaussian. So for that reason, sometimes free field theories are called Gaussian theories, because all the information is encoded in the 2-point function. So we call it sometimes Gaussian. The 2-point function contains all the information about correlation functions. And so this is for correlations involving the field, but correlators involving the conjugate momenta can be obtained from the previous ones by taking time derivatives. And and excited states. So if you compute the correlation function for a state which is not the vacuum but has some excitations, they have correlation functions which arise from vacuum bands by adding, as trivially, the correlations between the excitations. So for instance, if you compute the 2-point function for a state containing one single quanta with momentum k, you can check that this can be written as twice the real part of h bar e to the minus I omega delta t minus k delta x over 2 omega plus the norm of this state times the vacuum correlation function. Where this delta t and delta x is just the difference of time coordinates for these two guys, where x is tx and x prime is t plus delta t x plus delta x. So you can see that it's just the vacuum one adding some extra term. So therefore I say all this because therefore
You want that be 1? I mean, bra and fit of 1.
this is not 1 because they are not normalized. Remember, they are delta of 0. So this is why I don't write it explicitly. If you use wave packets, everything is fine. But here you have all these problems. So therefore, we can focus on the vacuum 2-point function. So this is the object that normally people study more in detail because this argument. All the other correlation functions can be obtained from it. So it is quite simple to compute the vacuum tubing function, just expanding the field and momentum operator in creation and annihilation operators. What we find, you can do it, is that the 2-point function, or 2-point distribution really, is given by h bar, is a quantum object, integrally momentum cube e to the minus I omega delta t minus k delta x over 2 omega. This is the formal expression for the 2-point function, and normally a good name is just g of x prime. This is just definition of this name. So you can see that this is just a sum in modes. You can check that this object is complex for general values of x and x prime and satisfies the wave equation. It satisfies the equation of motion, so the Klein-Gordon equation in both x and x prime. So if you apply the Klein-Gordon, box square minus mu square to this guy is 0 if you operate both in x or in x prime. Okay. I am giving you some details on this because of the statement that I want to make right now. So if x and x prime are spatially separated, so if you have x is here, you take the light cone of x and you consider 8 prime, x prime, which is out of the light cone, we can compute what is the correlation in the vacuum between these 2 points. So the value of the 2-point function, you can check. I mean, it's not trivial, but in that case, this integral can be done. And if I didn't forget any factor, this is given by the following: capital K 1 of m root square of x square, where x square, delta x, where delta x is a vector with components given by the difference x minus x prime. And K1 is one of these modified Bessel functions. And the most interesting part of this equation is that this is different from 0. So the statement here is that the vacuum contains correlations between points spatially separated. And I add a question mark here, I add a surprising mark here because this should surprise you. What about causality? What is going on with causality here? Before that, just let me that this is one of the main lessons. This is an important lesson in QFT. So, vacuum contains correlations, non-zero correlations between points which are causally disconnected. So the question is, what about causality? This is the key question.
Contribution will be too less, like correlation will be too less.
Will be what?
Too less in comparison to had they been
What?
too less. I mean, very much less. Like,
No, but if it is non-zero, it's non-zero. You know.
yeah, it is.
But if it's small, the causality, what is going on? You know, what
The
I can.
if you take the commutator of the two fields at x and x prime, their correlation function will be 0.
Are you happy with that? You should be happy because he's right. So this is true. This is true. I mean, there are correlations. The two-point function is different from zero. Causal is multi-point. So you know, this shows you that the vacuum is really something highly global. So highly global. You know, there are correlations between any points in a space, even though they are causally connected. The vacuum, you know, has, the information in the vacuum is between any pair of points. It's really like, like a spider net that is tied in every couple of points in a space. But does it mean that the theory violates causality? Not necessarily. So because in order to wonder what happened with causality, we need physical observables. So let me just write what we need for causality, and next day I will finish this, and we will start quickly with the next chapter. So causality is about observables. So how do we demand causality in a quantum theory? So in a quantum theory, so QFT is causal, so respects causality. If you take two physical observables, O1 and O2, O1 can be the energy momentum, angular momentum, whatever you want. Any physical observable at some point x. You compute the commutator with any other physical observable. At x prime, this is 0 if x and x prime are spatially separated. This is the way that we demand causality in our theory. So the question is the fact that there are correlations between these 2 points implying that this is violated? And the answer, of course, will be not. This will be true, this will be 0, even though this is different from 0. So that means that, when you compute observables, this guy will contribute, but there are other contributions that will cancel this one and give you a causal theory. So the fact that there are correlations between spatially separated points doesn't spoil causality at all in quantum field theory. So both are true. So this is an statement. What I have to do is to show to you that this is in fact true.
Do you mean the correlation function of the commutator?
It doesn't matter. This is true this must be true. It doesn't matter. This is always normally doesn't matter.
What do you mean QFT is causally something?
It's causal.
It's causal.
So I think this is the test of causality. We have to check if this is true. In fact, this must be true for any state. And
So you're saying that causality should be determined by whether the things are simultaneously measurable? because that's what we mean by commutative.
So what this equation means is that you have your intuition says that you can find a frame in which these two guys are simultaneous in a single frame, and therefore this equation tells you that whatever you observe in point 1 is not going to affect whatever you observe in point 2.
Because they can be simultaneously measured.
Exactly.
Okay, so they are not entangled.
Right. You can measure simultaneously both, but the one measurement will not affect the other. This is what this equation tells us, because
Okay, is it like they were not entangled or like, I mean, those-
entanglement is a more precise and has to do with quantum states. This is a operator equation. Of course, these are operators. So this is a state independent statement, and we have to see if that is true or not in our framework. And I advance the result. This is going to be true, even though this is also true. So this doesn't produce problems. And I will stop here. Next day we will prove that that happens. I will give you a bit of information about green functions, like the retarded and advanced grid functions, and the Feynman propagator. And we will finish the chapter, and we will start the harmonic oscillator for time-dependent situations, which is is much closer to the main goal of this course. You have questions there?
What does it mean for 2 points to be correlated physically? I mean, what does that physically mean, the fact that they can be correlated, being that this Green's function is not zero?
Right.
So I
Normally,
can compute this thing, and there's some non-zero value neat, but I don't really, what does that mean essentially?
so I mean, correlations come with a physical state. You have to give me a quantum state with a couple of correlations. And you can. The intuition is that the information in this point is not independent of the information in this point. There is some mutual information.
There's
between them.
information between spatially
Exactly.
connected
There is
points.
information between them. There is mutual information between them. This
Mhm.
all this entanglement in quantum mechanics that we can discuss.
Alright,
This
oh.
key.
So all points are correlated with each other.
Exactly. You can think about a particle of zero spin that disintegrates in in spin 1/2 or minus 1/2.
Mhm.
These guys are really correlated because the fact that this is plus 1/2 is because this one is minus 1/2.
Do
Quantum
two
entanglement.
different points on the null line, are they correlated as well?
This is a tricky question because the 2-point function is normally divergent on the null cone.
Oh,
So
okay.
you have to talk about distributions. You have to smear the 2-point function with a function of compact support and make questions there.
Oh, okay, sure.
Then you never had something just on the light cone. Yeah.
Okay. But I think the neat thing is that all points in space do have some sort of information shared between each other.
The vacuum, that
And that's not a local statement. Globally,
is a global statement. But we are talking about the vacuum. So correlations
Okay.
make reference to a given state. So
okay. Given one state.
the vacuum state has information which is correlated globally. So it's
Okay.
really a global state.
Does one excited state have spatially connected?
Of course, because it's the vacuum, I wrote it, it's the vacuum plus something else. So
Yeah,
this doesn't cancel the vacuum, so you have something
Okay.
on the top of the vacuum. But the key features are already in the vacuum. This is just the correlation between these two quanta,
Mhm.
which are the same one. So, but the key element happens there. And this is, I think, an important feature in quantum field theory that one has to realize from the very beginning. And second point, that doesn't violate causality.
Okay, so is it because like we are in free theory, I mean without any interaction picture, so we are using Heisenberg or
Is what?
like we are using Heisenberg picture?
We are using Heisenberg picture, but this is true for any.
Yeah, so is it because like we don't need to, what is that called, take into account interaction picture or something because we are in free theory or?
So you mean that in interacting theory this is not true? Or?
No, I mean it may be, but we might have to consider, like here we are talking just about observables, right? We are not taking state into account.
Right. But no, the statement is different. The statement is that if this is true, then you have no way to violate causality to theory. So this is the same.
Okay, like even if.
But it has to be true for any state. So I mean it's a strong statement.
Okay, yeah, any statement.
I mean this is just a state independent because this, but this really ensures that your theory is causal. So it's a big statement. And this is true for free and as well as interacting theory.
Okay, we just have to consider observables.
Exactly. I mean, because this is the way that you measure causality. You measure, there are many things that apparently violate relativity, like, that the galaxy expands in the universe 2 galaxies at a speed larger than the speed of light, but that doesn't violate causality. You have to measure things, you have to be able to communicate information. And this is the condition that you cannot communicate information between one and the other. Whatever you do at point X is independent of whatever you do at point X. Right.
Okay, so it may be like, observables, they are, what is that called? They are like separated, they don't violate causality. That is what. But it may be like something, like, what is that called? They might be entanglement or something like for states and all, but that doesn't affect this.
Right, you can have entanglement, but you can never communicate information with that entanglement. This is what this equation. So think about this EPR paradox. There is entanglement that you can never communicate information.
Are these time averages or spatial averages, or what kind of averages are, or averages over an ensemble of vacuums, or what?
Where?
Are
In which?
the expectation values,
You cannot think of them as a classical ensemble. They are the analog, but they are really quantum expectation values. So this is just the laws of quantum mechanics.
right, because I'm having a hard time picturing. Okay, so they're the expectation value associated with the quantum state of the vacuum. So.
Think about the harmonic oscillator. You have the
Right.
vacuum or one excitation, and you want to measure the value of x.
So I guess what's getting me is it translation invariant then, these correlation?
For the vacuum, yes. Because
Okay.
we proved before that the vacuum, in the previous section, that the vacuum is translation invariant. So the 2-point function is translation invariant. In fact, knowing the 2-point function has the same information as knowing the vacuum. If the vacuum is translational invariant, the 2-point function is translational invariant. It only depends on the distance between the 2 points. Doesn't matter if the points are here, you rotate them. But you are working with fields. This is what your intuition has to get there.
For some reason, I'm having a really hard time picturing this. Yeah, thanks.
This is field theory, so you have to sit down and think about what you are doing.
Where did the real part come from? That one? And it's correlated by being on a different phase from there.
That line of algebra is a little weird to me as well. How did we know to go from step 1 to step 2? Oh, damn you!
Does it solve your question?
Oh, that's bad. I wasn't
Any other
listening
question?
then.
Any other question, Penn State?
No.
Iwan, thank you.
Thank you.
Do you write 1K as a 0